In this lecture, we'll be discussing compound inequalities involving the connective word and. The intersection of sets A and B, symbolized with this intersection symbol right here, is a set containing all the elements that are common to both set A and set B. If you think about when you've heard the word intersection before in your life, when you're driving on a road, the intersection is the place where two different roads meet, that the intersection is right here. Now, that's what intersection is going to mean for us with sets as well. Intersection is the overlap of two sets. The union of set A and set B, the union symbol looking like this, is the set containing all the elements that are members of set A or set B. I always think of union as marriage. That's when we oftentimes hear that word union. That's where we're taking two people's things and putting it together into one house. So the union of two sets is just everything together all in one set. Given set A and set B, we want to find the union of set A and set B and the intersection of set A and set B. A union B. It's a set, so we want to make sure that we're using set brackets. And we just want to list all elements from A and B together. So in set A, that's -5, -3, -1, 0. Now we want to move over to set B and see if there are any elements in set B that we haven't already listed. I've already listed -3, I've already listed 0, but 5 needs to be added to the list. The intersection between sets A and B, that's the overlap. What numbers are in both sets? Is -5 in both sets? No. Is -3 in both sets? Yes, it is, so it belongs in the intersection. Is -1 in both sets? No. Is 0 in both sets? Yes, it is. The intersection of sets A and B is the set -3 and 0. A compound inequality is formed by joining two inequalities with a connective word such as and or. In this section, we're going to talk more about compound inequalities involving the word and. The solution set of a compound inequality with the connective word and is the set of all elements common to the solution sets of both inequalities. Therefore, it's the intersection of the solution sets of the two inequalities. We're going to be solving, graphing, and then writing our solution sets in interval and set builder notation. When we draw our graph, we are going to be looking for the overlap in shading. It was defined that our solution is the intersection of the solution sets, and earlier we discussed that intersection means the overlap. We want to start by solving each one of these inequalities as we would normally. So the first one, I'm going to need to divide both sides by 2. I get x to be strictly less than 4. And now I'll solve the other one. I'll subtract 3 from both sides, which gives me x is strictly greater than -2. I'm going to graph both of these inequalities on the same number line. I'll start with x is strictly less than 4. I find 4 on the number line. Here we are. X is strictly less than that, so that means that I'm going to be shading to the left, since less than is to the left, and it gets an arrow at the end. Since it was a strict inequality, we use a parenthesis at 4 to indicate that we're not including 4. Now we move on to X is strictly greater than -2. We find -2 on our number line. X is greater than -2. The greater numbers are to the right, so we're going to shade to the right. It gets an arrow on the end, and since it's a strict inequality, it's going to get a parenthesis at -2. That graph so far is not our solution. Now we want to look for the overlap in shading, because our solution is the intersection of these two solutions. The overlap occurs right here. So when you are taking a test or a quiz, you need to indicate that the part of the graph we're interested in is the overlap by either coloring it in extra dark or using a different color ink. Now that we have our graph, we want to write our set builder and interval notations. The interval notation, we want to start with the very smallest number that's included in that yellow shading. We want just larger than -2, so we write that -2 with a parenthesis to indicate that we're not including -2. And then the largest number included in our yellow shading is 4, and it also gets a parenthesis. The set builder notation always starts the same. It's the set of all x such that, and the x that we're interested in this time are the x such that x is less than 4 and x is strictly greater than -2. Notice that the condition we've written in our set builder notation is our solved inequality. This next compound inequality I call a sandwich inequality. The reason that I call it a sandwich inequality is because the variable is sandwiched between two inequality symbols. We're going to solve this inequality as we would if it was only a regular inequality. We can just cover up this part right here and solve it as if it was just -5x plus 1 is less than or equal to 6. If that was the case, we would subtract 1 from both sides. The only thing that we're going to do different here is that now we're going to subtract 1 from 3 sides. This gives us -25 is strictly less than -5x, which is less than or equal to 5. Continuing to solve for x, I need to eliminate that coefficient of -5, so I'm going to divide all sides by -5. Since we're dividing by a negative number, we need to remember to flip our inequality symbols. We get 5 to be greater than x, which is greater than or equal to -1. You'll notice that 5 is the larger number, but it's written on the left. I would definitely rewrite this inequality and write it -1 is less than or equal to x, which is strictly less than 5. This way I don't accidentally graph it incorrectly, have the wrong number first on my graph. To graph, I see in my solved inequality that x is trapped between -1 and +5. So when I go to graph, my shading is going to be between -1, and +5, because that's where x is, trapped between those two numbers. My inequality symbol over here is an or equals to, which means that I'm going to use a square bracket. This one is a strict inequality, which means that I want to use a parenthesis at 5. Our interval notation, our shading starts at -1. We are including -1, so we use a square bracket, just as we did in our graph. And then our shading stops just shy of 5. So to indicate that, we write 5 with a parenthesis. Our set builder notation always starts the same, the set of all x, such that, and our condition is our solved inequality. -1 is less than or equal to x, which is strictly less than 5. In this next example, I've already solved the inequalities for us. So there's my solution. We want to graph these. Graph the first one in red. X is strictly less than -2. I find -2 on the number line. X is less than that. Less than is to the left. It's a strict inequality, so I'm going to use a parenthesis at -2. Next, we'll graph x is strictly greater than 5. Find 5 on the number line. X is greater than 5, which means I'm going to shade to the right. Again, we have a strict inequality, so we use a parenthesis at 5. Since our connective word is and, that means that I'm looking for the overlap in shading. If you take a look at your graph, where's the overlap? There is none. Since there is no overlap, there is no solution to this compound inequality. So our answer is no solution. There's no interval notation to write. There's no set builder notation to write, since those notations represent our solution. The last thing I would like to do is an application problem. Juanita had a job offer to be an automobile sales position that pays $1,500 per month plus 2.5% of all sales. What total sales are required to earn between $3,000 and $5,000 per month? Since they are asking us to find the total sales required to earn a range, that information right there tells me that I'm going to want to write a sandwich inequality. I want my earnings to be between $3,000 and $5,000. Now we just need to figure out the expression for her earnings. She's earning $1,500 flat per month plus 2.5% of all sales. The sales is unknown, so that will be our variable. We get the inequality 3,000 is less than or equal to the flat $1,500 per month plus 2.5% times the sales. And now we solve this compound inequality. I'll start by subtracting 1,500 from all sides. Which gives me 1,500 is less than or equal to 0.025x, which is less than or equal to 3,500. Next, we divide all sides by 0.025. We end up with 60,000 is less than or equal to X, which is less than or equal to 140,000. That means that Juanita total sales must be between $60,000 and $140,000.